I'm gonna talk you about this kind of topics. This is part of my research that I am doing, I don't know, maybe the last 3 years. And I'm gonna to summarize in this talk. I apologize for my English. It's not so good, so maybe I make some mistakes. Okay, maybe this one. Okay, this is the outline of my talk. The very big topic is QED and QCD in extreme conditions. I'm going to talk about these scenarios related to this area. Basically, we started with the phase, an H is wrong here, the QCD phase diagram, and related topics like photon productions, how the screening properties of this media are modified by intense magnetic fields, temperature, density, and another phenomena, and some perspectives of our research. And what is QCD in extreme conditions? For our groups, extreme conditions are the conditions where temperature, density, and magnetic field are involved in the dynamics of these theories. In particular, we are interested in this conjunction when temperature and density meets together in what we call the QCD phase diagram. Also in the photon productions when density and magnetic field are involved. And when we have just magnetic field, we studied QED and QCD screening properties. And when the three big scenarios are involved, effective masses of gauge fields and fermion kind of particles. So in the very first topic, we have the QCD phase diagram. This is a conjecture phase diagram for a QCD matter. As you can see, for low temperatures or low energies, for high temperatures and low baryon density, we have that we call hadronic matter. Basically, quarks and gluons are joined together by the asymptotic freedom and all this stuff in QCD. And we can test this phase diagram experimentally with these experiments in this range of energy and density, the RIG in United States and LHC in Switzerland. Can test this kind of regimes, and they discovered this other phase, the quark-gluon plasma phase, and it's this phase when the quarks and gluons are almost free. And it's similar to the early universe. So there is a kind of phase transition from hadronic matter to quark-gluon plasma matter. And these other kind of matters, maybe a phase of matter, maybe the color superconductivity, quarkonic phase. These are theoretical predicted phases. We want to experimentally prove or disprove this. And these are the current experiments that will be available in the future. In particular, I wish to name this NICA in Russia, where my collaborators from Mexico are involved in these in detectors and theoretical side. We use compute some things about it. And there is a conjectured phase transition. The important thing in this scheme is in the high temperature and low density regime, this phase transition is almost a second order phase transition. Actually, it's a crossover, it's not a really phase transition, but from the theoretical point of view, for low temperatures and high net baryonic density, the theory say is a first order phase transition. So if you think that this cure is continuous or something like that, you can expect a critical point where the phase transition comes from a second order phase transition to first one. This point or this region is called the critical endpoint, and that's what we want to know, its localization and how it's modified by temperature, density, and other parameters. So in order to describe these lines, we know that the confinement transition, when the strong force is not enough to keep the gluons and quarks together, occurs in the similar lines that this kind of transition, the chiral transition, where we expect that the fermions of the theory become massless. It can be seen in this kind of Lagrangian. We cannot work in the full QCD pure Lagrangian because it's very hard to work with it. Instead of that, we work with this Lagrangian that is called the linear sigma model, this part coupled to quarks. It is a low energy Lagrangian for the QCD. We ignore gluons, we ignore some degrees of freedoms, we integrate it, and we end with this kind of Lagrangian. It has the same symmetries. Yes? I'm sorry? Yes?
Do we still have some strong evidence to the tranquility point?
I'm sorry, I didn't understand.
Do we have strong evidence to know what is the current status about the tranquility point? Is it crossover or it's not a crossover?
We know that in this region it's a crossover. I know that LSC can measure this part. Lattice QCD can measure in computational terms this region. Here we know that it's a crossover and it's kind of a second order phase transition. This is a conjecture. The theoretical models, the theoretical predictions say that here is a first order phase transition, and we think that this point exists. We are not sure. We need to measure.
So to make sure it's a lattice point or theoretical point?
Here is a theoretical point. Yes.
The second question is, do we have any experimental understanding to this point, even for indirect?
What kind of signature you are asking? Yes, we have some signatures from, if you want to study things like, I don't remember the name, I think the chiral magnetic effect, I'm not sure, but yes, from the theoretical point of view, you can expect some fluctuations in some parameters that tell you that this critical point exists. In particular, how is the transition? I want to talk later about it.
Okay.
Yes.
So they do a detection from the effective theory or really from QCD?
Oh, okay. I don't know from the experimental side. I mean, just theoretical, but maybe they can detect some things. I have no idea. Okay, this is a low energy effective model to describe QCD, and we couple it with quarks in a minimal coupling with these particles, and we have this field, sigma field, the pion field, and we gonna consider two light flavors that we expect that are in this kind of observables. The form of this Lagrangian admits what we call spontaneous symmetry breaking, giving us this kind of terms. And if we expect that, okay, we can say we are going to work around the vacuum fluctuations of one of the fields. In particular, we chose these fluctuations around sigma. We can do the same around the pion fields. The results are the same, but this is easy because this is a scalar, this is a vector, not in the sense of the field, but it has three components, I'm gonna say that. After we admit a spontaneous breaking, symmetry breaking, we end with this Lagrangian, and if you compare the two Lagrangians, in this one, fermions are massless. It's a pure chiral Lagrangian. And after this symmetry breaking, the fermions acquire some masses. So the masses of the particles after this replacement are given by these expressions, and you can see when the vacuum expectation value of this field becomes 0, the fermion mass is 0, so the Lagrangian becomes again chiral. So it can be a signature of this phase transition recording. Okay. Yes.
I'm a little confused because you have pions and also quarks.
Yes, yes.
So where is this?
Where is the what?
I would normally expect either like your light degrees of freedom are pions.
Yes.
So the quarks are confined into mesons.
Yes.
Or you're in a deconfined regime where the light degrees of freedom are just the quarks and not the pions and the sigma. Here you have both.
Yes. In a big picture, these particles here act like the boson-like of the theory, like a kind of gluons. This is basically, it is describing the residual nuclear force, and the matter degrees of freedoms are the quarks.
But you have pi interactions, right?
Yes, yes.
So there is like a mix.
Yes, it's a mixture of both things. Yes, when we integrate gluons and the pure QCD degrees of freedom, we end with a mixture. And it just works for low energy regimes. So this is, again, a kind of residual strong force or something like that.
You say low energy, like below what scale?
I think that's times the mass of the pion, and maybe for the energies close to the chiral deconfinement. Yes.
So if B vanishes, it looks like sigma and pi have negative mass squared.
Yes, this is not actually the mass of the particle. This is just a parameter of the theory. So in this regime, the mass becomes this parameter, and it's positive when B is 0.
Oh,
Mm-hmm.
oh,
What are the outputs of this?
I'm sorry?
This model, the outputs, the original outputs or references?
The original, okay, this kind of models is a copy and paste from the, what is the name? Condensed matter systems. You can find it in, I don't remember the name. Maybe I can give you at the end of the talk, the reference. Okay. So in that sense, when V is not vanishing, the fermion mass is not, the Lagrangian is not chiral. When it vanishes, is chiral, the mass of fermions. In that sense, we published this in this journal. We have two possible scenarios for the chiral restoration of the Lagrangian. In one side of the theory, we can see that this V is not 0, the mass is not vanishing, and some critical temperature, it can be 0 from continuously or not continuously, and it can tell us about the order of the transition. If I assume that this V is an order parameter of the theory, if I have this kind of behavior for V, we have a first order phase transition, and if I have this other behavior, I can be in a second order phase transition. How can we differentiate it from the potential? As you can see, I can read interacting part of this Lagrangian, and I can plot it against this variable V, the order parameter, and this behavior of the order parameter as the theory of the phase transition tells, if the potential has two minima in the critical temperature, it will be a first order phase transition, but it has a single minima, it is a second order phase transition. So this is the way that we compute this. We analyze the interacting potential at finite temperature. We find it.
Does a symmetry break at the transition?
Yes.
What symmetry?
Chiral symmetry. Yes.
So just the previous plot, you just consider the disorder plot.
Yes.
Could you consider the one loop correction without you just using the disorder plot?
We use quantum corrections in this sense. But
But you just write down the equation. But I can also directly compute the observables correlators
Mhm.
to see whether I can do phase transition.
Other observables, you say?
Yes.
No. We don't calculate this.
You say it's complicated or just troublesome?
We haven't tried it. I don't know if it's complicated. I don't know.
Because it's just correlated computation. It's not difficult, especially just about one loop.
Okay, I'm gonna. Good. Thank you. Okay, we have this potential for interactions of this in this model. We compute the partition function, and we use these quantum corrections for the propagator and self-energies of all the fields involved in this Lagrangian, and we end with this kind of effective potentials. This is a high temperature limit, and we have a temperature here and chemical potential. It can be done kind of easily. And this is our prediction for this kind of parameters. These are pure parameters of the theory. And analyzing by the interaction potential, we can say when our results are in a second order phase transition or first order phase transition, and we can locate approximately this the critical endpoint location. Of course, it highly depends on the choices of these parameters and this TC parameter, that is the temperature that the data or latest QCD tell us in this regime. So in principle, we can, with this theory, give some location for this order parameter.
In this also,
Yes?
what the lattice number you consider?
I'm sorry?
What the lattice number you consider?
What lattice data? This.
Lattice Fermi. Because your lattice data depends on what the lattice number you use.
Yes, the two light fermions.
The two is okay. You use the stagger fermion or overlap fermion or where's the fermion?
Okay, we just put here the lattice in order to compare with two light fermions. We are not concerned about what kind of fermions they use. We just want to know if this effective model can be related with some predictions.
Okay. The one issue is that if you consider Wilson fermion in 4 dimensions, indeed it does not have a chiral symmetry. It's very possible not to have a chiral symmetry even if you take a complete limit. So in this sense, if you just apply the Wilson fermion to this plot, it's hard to see whether you have a chiral symmetry translation. Is one issue. Another thing is my curiosity. Why don't you just use give result? It's hard to do.
I think so. From this Lagrangian and this treatment, I think that is hard. I am guessing. Yes. Okay. And this is all results, these black dots, compared with other kind of models. I don't know, maybe Nambu-Jonalasini or Polyakov models, these white dots, and some predictions for lattice QCD. So in general terms, this approximation can be compared with another with another models and theories. I'm gonna say again, this is an assumption that this point exists. So when we have maybe in the future experimental points, we can compare which one is the correct description of these kind of systems. Yes.
Do you know if people are planning experiments?
Yes, for example, the Russian people with Nika.
Oh.
They want to run lower energies in order to have finite chemical potential.
Great.
So this is going to be the good scenario for that.
I heard that last week from somebody else.
Okay.
So this is the state of the art as far
Yes,
as
this is the state of the art. Yes. We don't know where is it and if it exists. Maybe it doesn't. We don't know. Okay. In the other side, we want to study this when density and magnetic field are together, in particular with these kind of observables, photon production. And why this is important. This is a scheme of the heavy ion collisions. When two heavy ion collide peripherically, we have several phases here. We have a pre-equilibrium phase. It is full of gluons. After that, the system begins to thermalize and expand it. We have QGP phase, quark gluon plasma phase, and after that, it becomes too cool and expanded, and these are the final observables. And in all these phases, photons are produced. This is one of the most particles that are produced in this kind of experiments, and you can track and say where they came from. In particular, we are interested in this region because there are models that doesn't satisfy the experimental data in this sense. We can compute all the photons in several stages of the collision, the very early thermal phases, when the system cools down and expands, and another kind of photon sources. But when you compare, and this is an old plot, I have to say, you can, the people measures this invariant momentum distribution of the photons against this transverse energy, and those are the experimental data. And you have to watch this, the black one curve, that is the sum of all the photons. This is a weighted average of all these photons. And you can see there are a huge discrepancy between theory and experiment. Also, if you look for the harmonic coefficients of these measurements, basically how they flux in the space, in particular this B2 coefficient is a kind of ellipsoidal flux. Again, you have to watch. This is data for Phoenix, and this is data for LHC in Alice. This is the curve that you have to watch, and you have very strong discrepancies between theory and experiment. Direct photons are all the sum of all photons. It's not a direct sum, it's a weighted sum. So it's not just at this one. You have to.
The solid lines are the theoretical.
Yes, or are theoretical. Yes. And when you compare these kind of fluxes, the B2 harmonic coefficients, again, you have to watch this curve. This is just pure thermal photons, just for reference. And you can see for Phoenix and Alice that you have several discrepancies. Maybe you can say for Alice is more or less okay, but okay, this is a huge error bars, and we want to be close to the central points maybe. So there is no enough photons, let me say like this, for describe this experimental data. And we are looking for another mechanism in order to get more photons. In particular, we want to explore these regions where another dynamics is happening in these collisions. In particular, we want these regions because we know that gluons are dominant in a small X region or high energy region, basically this pre-equilibrium region. You can see in the PDFs, this is for gluons, it is scaled by 10, and this is gluons. So we start with an initial phase full of gluons, and also we have magnetic fields in this region. As you know, maybe the collision is not always central, it's peripheral, and this is a region of collisions, but here you have electric currents that makes magnetic fields in this region. And these magnetic fields can be simulated, and this is a kind of a spatial and time distribution of these magnetic fields. And you can see this is 4 times almost the pion mass square, that is kind of this large. A neutron star is about 10 to the 10, if I'm not wrong. And this is a huge magnetic field. But as you can notice, this is a short-lived magnetic field. So in this regime, we have a region with high density of gluons and also high magnetic fields. So how can we mix this together? We propose this kind of photon productions. We have gluon fusions and gluon splitting. In the final state, we have one photon, and as we know from the QED pure consideration, this diagram is 0, is vanishing in the vacuum, but when we consider magnetic fields, it violates the Fourier theorem, and this is they have a probability to occur. So we can relate just like we do in quantum field theory, and when consider this, okay. Yes, in the vacuum, these diagrams and its conjugate are not related by a minus sign. It doesn't apply. Yes, you can. Yes. Okay. The single lines are. Okay, let me show you the expression. And this is our diagram. It can be written in terms of the common propagators. And these propagators, when we consider a constant magnetic field in some direction, this is a propagator that has this spatial dependence, and you can write it in terms of Landau levels. We have an infinite sum of Landau levels given by this index n, and depending on the n, we just find a single line for the lowest Landau level, a double line for the first excited Landau level. As
QCD, you have gluons, and then the quarks are populating Landau.
yes. Yes.
This is QED.
Yes, QED, and the QCD part is just this trace over the Gell-Mann matrices. Yes.
Principle, the magnetic field is going to contribute much more in the chromodynamics contributions, right? The coupling is 10 to the 2.
Yes. Okay, no, this is pure QED in the sense that we are just considering a magnetic field that couples to the quarks by electric charge. The QED part is factorized.
This number, I don't. The expression comes from.
Which one?
The Euler-Heisenberg-Lagrange.
This one?
Yes.
Yes, it's the Schwinger propagator, basically. Yes, a constant field. Yes.
Is the phi in front of the propagator?
When we compute the propagator in the Schwinger's form, we know that it depends of the space-temporal coordinates. This is called the Schwinger phase, and that's because the magnetic field breaks the Lorentz symmetry. You have a remaining of the coordinates in that propagator. This is a This is a well-established things when you work with magnetic field.
Phase factor is a contour. What contour is that?
It's any contour that you can draw. In particular, we chose sometimes a straight line in order to, when we have some gauge, when you fix the gauge, you can have any contour.
Then it depends on the contour, the calculation.
Yes. When you don't, okay, let me think about it. No, it doesn't depend of the contour. Why not? I have not here. Let me think about it. Yes, I have to think, but I know that it doesn't depend of the contour, and just this term you have to fix the gauge in order to show that. I remember this. Okay, so we have a sum of all the Landau levels given by this magnetic field. And in this approximation, we want just to have the first Landau level and the lowest Landau level in order to have answers about intense magnetic fields, because extra Landau levels are doesn't contribute in this expression in first approximation. Of course, you can have a sum of all the levels. People do that, and for, I don't know, maybe for weak magnetic fields, it can be done. So we can compute this amplitude. We can zoom for all the direct photons that I previously showed you, and this is all results. This is for these energies, and just considering this is the magnetic field used for spectators, the particle that doesn't collide, and this is considering the magnetic field made for spectators and participants. And for a low energy regime, we did some approximations for low energy in order to have analytical expressions. It's well described in some part the experimental data. And this is compared with another kind of centrality for, I don't remember, compared with this data. And we see that these new kind of photons added to the other ones well describe the data. So
This is for a constant field, right?
yes, use a for a constant field.
But you showed in a previous plot that
Yes, this is work in process. It's very hard to have these spatial and temporal contributions of the magnetic field. Yes, of course. We have to do that. It's difficult. Okay, and this is the result also for the magnetic field just made by spectators plus participants. For the B2 coefficients, I have to say again, for high energy regimens, we cannot say anything because we did some approximation. So this is our range of validity. And we can see that somehow this can be well described the data. So this is a photon source that we want to express in these terms. And the key point is to watch if these magnetic fields have, if the initial stage of the heavy-ion collision actually had these magnetic fields. Otherwise, this is just theory. Okay. And also with these results, we can predict how these photons can flux. This is the azimuthal angle that these photons can be detected. So in terms of the magnetic field, we can expect this kind of flux for these photons, and maybe it can be a signature for future occurrence experiments that wants to measure the effects of magnetic field in these situations. Yes.
So it's saying that smaller magnetic field, they're coming out around peak is near 0.
Yes.
Then it starts to spread out.
Yes. Okay, this is for photon productions. And when we, inspired by these results, I have to say that we have several issues in the calculation, and it becomes in this research, and the issue is the following. When we have this kind of diagram, we want energy and momentum conservation, and basically the three momentum of the parent particles must be parallel with the photon momentum. And this is an issue because when you want to compute the cross section, it is divided by 1 over the relative velocity of these particles, and these particles are gluons and photons. It travels at the speed of light, and this property makes that this velocity is 0. So we want to know if this dispersion relation can be modified by the screening properties of the media. In particular, we want to develop a magnetic mass in order to break this condition of the momentum parallel for these particles. So in order to compute a mass correction of these screening properties, we compute the polarization tensor for photons or gluons is the same. The QCD part is just the trace of these gamma matrices. So we have the two contributions in this diagram. It was reported in these papers. And this is the expression. Again, we use the propagators in an intense magnetic field, and we computed for all the Landau levels. We sum up all the Landau levels, and we end with this kind of expression. These are coefficients, very ugly coefficients, but the interesting part is that all these tensor structures, this one, are transverse in the sense of the Ward-Takahashi way, but these other are not transverse in that sense and violates the Ward-Takahashi identities. If it is true, the U1 symmetry is broken, and the photon is massive in that sense. But we can demonstrate that these coefficients are vanishing and the Ward-Takahashi identity is recovered. And this is an interesting point in the sense that the people that do this kind of diagrams or sums over Landau levels ignore that a simple sum of that levels give this kind of terms. So the literature about this kind of sums must be revisited because they will add up this kind of tensorial structures. So with just pure magnetic field, photons kind of developed magnetic mass. This is a discussion that this is in literature, and we demonstrate that the U1 symmetry is again recovered. So we are still looking for effective masses. So we have these three contributions. We expect that another masses became from them. So we compute these kind of diagrams for the photons and gluons, and for the fermions of the theory, the self-energy. And we want to compute it with temperature and magnetic field and density. So this is our contributions about it. Yes?
Previous case, was that just with the magnetic field?
Just with a constant magnetic field, photons and gluon doesn't develop in mass.
No temperature, no density.
No temperature, no density. Yes.
Do you have any intuition for why you need the whole sum over the Landau levels to get 0?
What we need?
Yeah, why? I mean,
Why?
I include like 10,000 of them, but not all of them.
Okay, you have to add it up all of them because you need to know. Okay, let me say that way. each lambda level contributes with some tensor structure of for the fermion propagator. You need to add up all of them in order to complete the picture of all the physics involved. Okay, you can sum just few of them. The people do that computationally, but each term that you sum is adding some kind of term in this tensor and this other tensor. So we wanted to add all of them in order to know how much is increased this tensor and this other tensor.
Different levels contribute with different signs?
Yes, it's alternate sum and all this stuff. So, but when you added up all of them, we can demonstrate that these integrals are actually zero. If you stop, it is not zero.
Now you're going to turn on temperature and density.
Yes.
Even if you don't have the quark loop, the electron loop, you still have corrections to the dispersion relation, right?
Yes.
And these are included in the analysis?
In this analysis, no.
I mean, it's the first one you have to include.
Yes.
Plasma frequency.
Yes. You can add it. Yes.
But that solves the problem you were commenting about, because I didn't understand the previous slide about this.
Which one? Yes.
What is the issue here?
The issue is that the three momenta of these particles are parallel and they'll travel at the speed of light. And when you have the cross section, you have 1 over the relativity speed of these particles, and it becomes 0. So you have, in principle, 1 over 0. When you no, we don't have idea what's happening. We want, first of all, that the magnetic field may modify the masses, but it's not an infrared divergence or something like that. It comes just from this condition of the energy momentum conservation. It's an issue that we want to solve. And the answer maybe is because we are considering a constant magnetic field. If the magnetic field is not constant, I will show you that this thing is broken in some sense. Okay, and okay, we want effective masses from these kind of diagrams, and we found the following. This is this is the effective mass for fermions. This is rediscovering the hot water, basically. I don't know, in the 60s, some people compute these magnetic masses for fermions. It depends on the spin projection over the magnetic field direction. And this is done for a very huge magnetic field. We want, again, to sum all the Landau levels. Sum all the Landau levels is the same that to say we consider it a weak magnetic field, intermediate magnetic field, and we have corrections for that expression that looks like this, the blue one and the red one, from projections parallel and anti-parallel to the magnetic field, and it is related to a real part and imaginary part of the mass. If you have an imaginary part of the mass, you can expect that this system is not stable, and we can looking for a spectral density for the propagators and these particles. This is the new contribution. The magnetic field makes that these fermion modes that propagate are not stable, and they have a spectral density and a spectral width related to the intensity of the magnetic field. So we can expect that these kind of decays that are related with this may be measured in order to have a signature of the magnetic field existence. This is for magnetic field driven masses. On the other hand, okay, I'm sorry. Okay. All this summarize things that we have done in equilibrium. We have a constant magnetic field, constant temperature, a uniform density, and we asked how can one describe this phenomena outside of the equilibrium. So we have to do another techniques in order to compute this kind of quantities. And why we want out of equilibrium scenarios. Okay, in the early stage of heavy ion collisions, there is nothing constant there and homogeneous in this kind of collisions. This is a energy density, for example, when two heavy ion collides, the magnetic field is not constant. It has it evolves in the space and time, and the energy density, for example, in this and the fluxes in a quark-gluon plasma or something like that, it have several irregularities in the space and time. So we want to add all this phenomenology to our calculations. Yes?
So the magnetic field is really big, but only until like
3 fermions.
0.2 Fermi over C.
0.1. Yes.
Then thermalization is later.
Yes, 1 Fermi, 2 Fermi.
1 or 2.
See.
Okay, so then all this stuff happens.
Yes.
Working with that. So
Exactly. Yes. A study of maybe December last year suggests that when you consider the what is the name? I forget the name of some parameter of the quark-gluon plasma, this magnetic field can be live in the thermal stages. We are working on that, and I think I can show you some results about it.
will it show up like in the initial condition?
I'm sorry?
Will the magnetic field affect the initial condition of the quark-gluon plasma?
Yes. Yes. Okay. And how we can do that? We gonna use this trick, the replica trick made by Parisi, and this trick is simple. It was used in condensed matter systems in order to describe spin glasses, and the idea is if you have irregularities, perturbations, defects in your system, you can average them in this way. You average over all these defects, and you can compute an effective Helmholtz free energy for your system. And using this limit, this is hard to compute. This is easier to compute. This z over up to the n, and you take the limit, and you can find your natural logarithm for the partition function. We have the same for I don't know, maybe the generating functional of the quantum field theory, and we're gonna use this trick for our calculations. Our starting point was the fluctuations of the magnetic field. This is our simulations of magnetic fields, this one up here. And we can see that the magnetic field fluctuates in the space and time, and the fluctuations are above, I don't know, maybe 1 point or 2 points the pion mass squared. And we assume that this fluctuation can be described by a term in the Lagrangian. When you have the 4 potential, you have photons, you have a constant magnetic field that we consider as a background, and fluctuations around, classical fluctuations around that background. And these fluctuations are white noise fluctuations. White noise, it means that it has these statistical properties. They are in average 0. And we can, from this analysis and looking for how is the geometrical form of the collision, we can test that this correlation measure of the fluctuation can be of this magnitude.
So you're splitting this is an abelian gauge field.
Yes.
And you're splitting it in a background.
Yes. Fluctuations. and quantum pure contributions.
But that will be a mu equal to a mu background plus
Yes.
field.
Yes.
The thing that is written there.
I'm sorry?
Not the thing that is written.
No.
There is a type. I mean, you have three fields.
Yes. This is the pure quantum corrections, photons. And this is our classical fields.
And the delta.
The delta is a fluctuating classical field.
And the first one also fluctuates.
This one, no. Okay, it fluctuates in quantum form, not classical. This is a space-temporal fluctuation, not a fluctuation in terms of quantum mechanics.
So you're assuming one of those fields is constant.
This one, the background field. We have,
Doesn't depend, right?
yes, maybe I cannot write this. In general, it's this, but for our application is independent of X.
The other one only depends on the space and not the
We just want to analyze spatial fluctuations. In other words, we use spatial time fluctuations. In particular, for this analysis, we use spatial fluctuations because in X, Y, and Z, there are fluctuations in this magnetic field. Just in particular for this work. No. And in order to don't have all this discussion, we use average with the replica trick. Okay. In order to put this in our Lagrangian, we use minimal coupling, the QED Lagrangian with this for potential. And again, this is a white noise statistics that can be mapped to this distribution function. And this is a Gaussian. This is good. And when we average this Lagrangian, the action of this Lagrangian, with this distribution function, we end with an effective action. And this effective action is writing like this, which have a pure QED Lagrangian, as we expect, and an effective interaction driven by this fluctuation parameter, delta V. And this is what we call a replied Lagrangian for the theory. You don't have fluctuations. Obviously, you recover QED with the photon field and the background field as usual we have. So with this effective Lagrangian, we compute corrections to the propagator self-energy of the particles. And our vacuum or all reference propagator is the propagator of a fermion in a constant magnetic field, the Schwinger propagator that I previously showed you when we analyzed the photon production. And this is our results. This is the renormalization factor for the electric charge that depends on the magnetic field and the momentum, the energy, I'm sorry, of the fermion. And giving this, this is a parameter that says that how strong is the fluctuation. This is how the electric charge is modulated by the fluctuations. And also the velocity transverse to the plane of the magnetic field. And you can see, okay, this velocity is different from 1. That if it's 1, the velocity is not renormalized. And it tells us about birefringence effects in this system. It means that the fermions moves in several, the velocity of the fermions depends on this energy, and we can have different mechanisms of photon productions, and the medium is an active part of the movement of these fermions in the fluctuating background. Also, we analyze this effective action in terms of the bosonization framework in order to know what happens with this with the Lagrangian when we have this kind of interactions, and we show that there are currents, fermion currents, that also breaks the 1U symmetry, and we expect that these vectoral currents impacts on the polarization tensor and that other stuff that I'll tell you later. In what sense? And if we want to compute the corrections for the mass of the photons, given that this is not Lorentz invariant, as you say, and we compute that this breaks 1U symmetry, the photon mass is corrected by effects of the magnetic field with fluctuations. I mean, the magnetic mass of the photon given by this is corrected by these parameters. It tells us about the fluctuations, and this is the correction of the photon mass. So in principle, we have a mechanism in order to avoid that issue that I told you in the photon production part, and this is because the magnetic fluctuations. So we have a finite mass for photons. On the other hand, we compute the magnetic correction to the fermion mass with this kind of fluctuations. This is fluctuations, give classical fluctuations. Those are quantum fluctuations, pure photons. And we rediscovered that there are quasi-particle modes, and the weights of these modes are separate for its helicity and the projections of the spin over the magnetic field. So it might be a signature for fluctuation of magnetic fields if these fermion modes decay. And also we compute how is the photon and the electron production, and in the quark-gluon plasma phase. So this is the results. I don't know, this is for December of the last year. If you consider some properties of the quark-gluon plasma, the magnetic field can survive in this stage, in these times where the quark-gluon plasma phase is created, and when the system thermalizes. We have a finite temperature here, and we have a small magnetic field that fluctuates, oscillates, basically. So if it fluctuates, maybe this theory that I show you may apply, and we compute the photon production rate with this kind of diagrams. The imaginary part of this gives you the photon production by part annihilation of quark-antiquarks, and I'm sorry? If you consider the, what is the name? It's a electromagnetic field, electromagnetic property of the quark-gluon phase. I just forget the name of this quantity. The conductivity. The conductivity of the quark-gluon phase. The previous result that I showed you of the magnetic field, we don't consider that conductivity. When you consider that, they show, this is not our work, this is a work of other people, they show that the magnetic field can still oscillate in the quark-gluon plasma phase. Why? I don't remember. Why?
Because the spectators.
Yes, they are far away, yes.
This must be some internal.
Yes, okay. The quark-gluon plasma phase is made of quarks, and they can, I don't know, producing small magnetic fields. This may be the physical picture of that. And it oscillates, okay? We, in first approximation, treat it as a fluctuation. This is an oscillation, not a fluctuation. And we want to know what happens if we consider that. And this is all results of the fluxes of the photons in several directions. The B2 coefficient is not modified, but the higher harmonics are modified by the fluctuation. The red one is with fluctuations, the blue one is with a constant magnetic field. And we expect that fluctuations can be measured by these flow coefficients in the several directions. So you have photons coming for another parts that the theory in the constant magnetic field tell you about it.
Hydro simulations?
I'm sorry?
These are hydro simulations for...
Yes, this is not mine. This is just a motivation for this kind of plot. You have a B2 coefficient is a flow almost in a ellipsoidal way. B3 is a triangle. B6 is a 6-point thing. This is you can. I'm sorry.
Hydro with an oscillating magnetic.
This is just hydrodynamics without magnetic field. And this is our results with magnetic field constant and fluctuating magnetic field. And they can be also be modified by not just for the fluctuations but for the energy of each photons. So you have a superposition of these two elements: the fluctuation of the magnetic field, the energy that you detect for the photon, and it will tell you about the fluctuations and the anisotropies on the magnetic field in the quark-gluon plasma phase. Also, we want to know about thermal fluctuations, and we use the same trick for computed the average partition function with the replica trick, and we let the temperature fluctuates in the same way that the magnetic field fluctuates. I mean, in a white noise fluctuations, and we can compute analytically all the partition function for thermal fluctuations. We can write the grand potential for this theory for fermions and bosons of the theory. This is analytical computation, and we did a small analysis in where we want to compute the pressure before the chiral transition or the confinement transition, and the pressure before this transition. It must be continuous, and it can give you the pressure in both regimes, and we say they must be equal. We found that the temperature for the transition from hadronic matter to quark-gluon plasma phase may be lowered if you have magnetic fluctuations. Temperature fluctuations. So it can be an extra signature of the fluctuations in this kind of systems. Another way to handle with fluctuations is this ansatz. It's called superstatistic. Basically, you have fluctuations in your system, but locally they are in equilibrium. So you propose a modified Boltzmann factor that is made of average of each Boltzmann factor. This is an ansatz. This is a good idea. It works in some scenarios, so we tested in this kind of system. In particular, we shows that there are fluctuations of positive quantities, basically a gamma distribution. We can compute analytically this kind of Boltzmann factors, and also we can compare with the replica trick form. It has a similar form of the replica trick, but with the difference that the replica trick considers the microscopic interactions, and this kind of approximation doesn't consider these interactions. So when we do that for the linear sigma model, in order to know how the chiral transition is modified by thermal fluctuations, we found the following. The lines of the transition compared with the constant temperature case are not modified, but the location of the critical endpoint is modified when you consider fluctuations in temperature. Actually, the considerations of the fluctuations of temperature make that the partition function is volume dependent. It's not, it is an additive thermodynamics in that sense. So when you modify the volume of your system, the critical endpoint moves, but the transition lines are the same in our approximation. And this is maybe interesting for someone, I don't know. Okay, as a conclusion, we developed several formalisms in order to handle with some observables in equilibrium and out of equilibrium. And we hope that these observables can be interested by the community that do experiments. And we are waiting for current experiments of lower energy, in particular NIC experiments, in order to know if the critical endpoint exists, more statistics about the photon productions. And this is all. I'm sorry again for my basic speech, but thank you very much. Okay, questions or comments? Yes. Okay, we are thinking about considerations about the early universe in order to consider fluctuations in temperature and magnetic field. Maybe some signatures in the polarization of photons that some people are trying to measure. We are looking for that kind of signatures.
Do you think it can affect the phenomenology of QCD at even like way before the confinement phase transition?
Away from that, I have no idea in this moment. I can think about it.